Hello, everyone. Yeah, welcome to the new Windows on radio sources breakout session in the meeting. So let's start this session, and we have 4 presentations in this session. So the first one is given by Barrett on the new development element of hops 4. So John, you are here. Yes. So please share your screen and start your presentation. Yeah.
Okay. Here we go.
Okay. Yeah, I will give you a reminder when you have 2 minutes left, and then we will have 3 minutes for discussion. Okay.
Okay. Great. Can everybody hear me? Okay.
Yes.
Okay. Awesome. So I'm just going to give you a brief update on the hops 4 development that we've been working on for the ngEHT. There's probably a little bit of a change of pace from the rest of the talks in this section because it's a more nuts and bolts discussion of a software refactoring project than science, but hopefully still interesting for you. So I just want to start off with the overall goal of our project here, which is to upgrade and replace the existing hop software with a more modern version that preserves all the existing functionality, but refactor all the backend so that we can make it satisfy requirements for the ngEHT and enhance the ability to extend the software. So I'll give you a brief background on hops, what the software architecture and features are, and the limitations of the existing software, fill you in on our development roadmap, and give you an update on the current state of the project. So hops, if for those of you who don't know, is the Haystack Observatory post-processing system. Its primary purpose is to provide ability to calibrate and manipulate the data post correlation. Primarily, this is fringe fitting and other forms of data flagging. It's had a very long history. It was developed back in the early 90s by our now director, Colin Lonsdale, Roger Capallo, and Chris Neal. And a lot of the algorithms that were implemented were originated even before that, back in the 70s from Alan Rogers. It's gone through many periods of redevelopment over the years. In the early 2000s or mid 2000s, it was adapted to work with software correlators like diffx. In the 2017 EHT campaign, it was augmented with a series of Python scripts to steer it and help it work well for millimeter VLBI. If you're interested in that, you can check out Lindy's paper. Hops is a collection of programs, but its primary mainstay, I guess, is the fringe fitting software forfeit. But it also includes other data summarization executables like A-list and ngEHT for diagnostics that are heavily used during the correlation process itself. The existing software architecture is composed of these 3 main applications, plus a handful of other minor utilities. I won't go into the details of all these other utilities, but it's not very well segmented. There's a handful of low-level libraries that handle some system utilities and input-output, but it does not, the executables themselves are rather complex and exist as monolithic applications. So refactoring all the software requires breaking up these applications into more limited libraries that have a well-defined interface between them. So part of the drawbacks in the existing software architecture is that the fringe fitting is really a one-shot process. The corrections you want to make to the data need to be known a priori, and if you don't know them, you have to go through this iterative process of refringing the data, applying corrections, and try to steer it towards the fringe solution. And just because of the way it's evolved over the years, extending this is becoming more and more difficult as time goes on. And we've really reached the limit of what we can do with Band-Aids, being small changes that we can, Band-Aids being small changes in the code and additional control file features that have been added over the years. So these things are starting to become a little impractical. So the technical limitations of the existing software are that primarily stem from the fact that our dynamic memory application is really rather limited. All this code is written in C, and while there is some dynamic allocation that's possible, a lot of the code depends on statically sized arrays. And you can continue to bump these up over the years, but it's not a practical solution long-term, and it needs an upgrade to work with the ngEHT. There's no ability to do fully complex bandpass corrections. It's only really per channel phase and delay corrections. And the fringe finding algorithm is a single scan, single baseline algorithm. It's very robust and deterministic and has a lot of knobs you can tweak, but there is no multi-baseline treatment at all. And apart from that, in the current age, it's a little, it is a bit of a drawback that there's no real multiprocessing support in this. So you have single program, multiple data style parallelism that you can fire up when you have embarrassingly parallel jobs. So you can fringe fit multiple baselines for multiple scans at once, but there's no other more complex parallelism than that. And the other practical limitations to the existing software is that the control file syntax is pretty arcane. It's not something that anybody would immediately recognize if they saw it. The data treatment is rather limited. You can really only access it through what is exposed in the control file. And the data and filing formats are not easily modified, and they're pretty tightly coupled to the existing code. In addition to that, we have a reliance on a handful of what are now unmaintained libraries, namely pgplot, that prevents a simple installation for people who are relatively unfamiliar with building the software package. So the existing architecture is going to be improved, and the new software that we're planning on building is going to be more of an object-oriented component-based design. And the libraries should be much more loosely coupled, and the applications will be built out of those libraries. So at a bare minimum, it's going to support 30 stations and 128 channels, but these are really just minimum numbers that we had to throw out there to say, yes, we could do this. Really, the only limit on the amount of data you could process will be what the system memory you're working on is. So the existing software is going to be refactored into libraries, and some portions of that will be reused. But the ongoing HOPS4 project will be a multi-language project that involves the old C code, new C++ code, and Python as well. The primary ways for extending the software, the HOPS4 software, as it goes forward, will be through developer extensions, compile time extensions, which would be building new data operations that inherit from a common interface, and runtime extensions, which we plan to provide via Python plugin interface. So there'll be bindings to the data containers and the data operators, and users will be able to interact with those during fringe fitting and other operations that you might perform on the data. We also expect that the HOPS4 installation process should be much more straightforward and require a much fewer number of dependencies, so that it should hopefully simplify containerization. I won't go through this entire list of libraries that we're building, but the existing C libraries are the legacy C libraries will continue to exist, and we will be able to build the old applications. Forfeit is going to be broken up into several libraries, and so we can reuse some of the existing routines. And the new C++ libraries will be composed of really task-specific things like the data containers, utilities, math routines, messaging, interface to the old data types, and the new calibration routines. Just to give a rough idea of what the overall architecture is in dependency space, so how the libraries all rely on each other. We have this large tangle of libraries that come from the original C code that is forfeit, essentially, that's been broken up into several pieces. And over here, we have the new libraries that should have a much more uniform hierarchy. And there's only a very narrow coupling between the two systems, the old data and the new data. The old code and the new code, which is through this Mark IV interface, which allows us to import the old Mark IV data types into the new data containers so that we can manipulate them with the newly developed software. So the legacy code really operated very heavily with these Mark IV data types to organize the data. And we are now moving to a more flexible and dimensional template class that will support a variety of objects. So that would be the visibilities, the data weights, flagging tables, et cetera. All of those n-dimensional arrays will have coordinate axes that will label what the time frequency and polarization product and channel are, and so on. and we should be able to label individual chunks of those data arrays with key value pairs. So I think it's a much more uniform interface for how we treat the large chunks of data, and doesn't require all these very difficult to modify nested C structs, which is what the Mark IV data looks like. The trivial metadata that's stored in the VEX file will be transitioned into a JSON format. So it has a much more uniform interface for accessing the various bits of metadata. And all of the manipulations of the data will proceed through a uniform interface of operators, be that unary operators, binary operators, etc. So the things that you do to modify the data, be that applying phase cal, etc., or will all look like a similar type of operation that you do. So you can build the operator and then insert it into a series of slots so that they can be executed in order. Just to provide a brief overview of what the simplified fringe fitting architecture will look like. We expect
2 minutes.
2 minutes, okay. So it will proceed a lot in the same way, but we are going to provide the ability to insert optional scripting from the user. So you'll read in your data and your configuration about what operations you want to apply to the data, but at individual discrete points, you will be allowed to insert your own Python code that may modify the data in place or configure data operators that are exposed via the bindings. So once you read in the visibilities, you can apply standard corrections, normalization, and then you'll provide a hook to do some customized data flagging. And then once you've done with that, you move to applying bandpass corrections, and then you'll be provided another hook to insert a customized script. So these sort of optional user scripts will be there to provide features that we cannot provide ourselves or haven't had time to implement yet, or allow users to do things that are experimental. So where are we on the development roadmap right now? We've put together the new build system and the testing infrastructure. We've imported all the hops3 libraries and most of the executables. They're not frozen yet, but they are being maintained synchronously with the new development. We've implemented our data container formats and written at least a conversion library so we can import the old Mark IV data. diffx import is not yet there yet, but we're working on that. We've populated a lot of the basic data operators, and we are in progress in building out the rest of the calibration routines. So what remains to really be done is to implement basically our forfeit replacement from these data operators and continue the build out. Eventually, once we have gotten far enough along that, we will also augment this with sim parallelism like OpenCL and MPI so that we can provide memory scalability. So the current state of things is that HOPS3 is operational. It will continue to be maintained for several years. And a lot of the key technologies in the HOPS4 development process have been demonstrated. And as we continue to build it out, we'll provide updates in the future. So thank you very much. Mark, do you have a question or?
Thank you, John. Yes, I think Mark raised his hand first. Mark, please.
Thank you. John, do I understand correctly that if you use diffx import, you skip diffx to Mark IV and just read the diffx output directly? Yes, yeah, we'll be writing a separate diffx import executable that will avoid diffx to Mark IV entirely. We don't currently have that yet, but that's in the works.
Okay, so next question, Mikhail, please.
Thank you. Hi, John. So I have a general question. So the upgrade of hops, do you have specifically ngEHT in mind, or do you also want to have it as a more generic software package that also can be used for other VLBI arrays, geodesy, and so forth? And as a follow-up question, do you also specifically for ngEHT, do you have some specific development goals in mind? For example, specifically tailored towards the multi-frequency receiver capability that we might have?
So I'll answer the first part. So we do plan to make this the software to provide support for multiple types of arrays. So the support for Vigos or geodesy will also continue through hops 4. Obviously, what the refactoring we're doing needs to happen in order to support essentially the existing hops functionality for data that comes from the ngEHT. So while I don't think in this project we don't have plans to specifically focus on, say, like a 3-band processing data from a 3-band system, that should be enabled by this project. So this is mostly focused on refactoring the software so that we can make it extensible and add new features like that.
Okay, thanks.
Okay, thanks. Thanks, John. Unfortunately, I think we need to move on. So if there's any more questions or comments, could you please move to Slack, please? Yeah. Okay, then our next speaker is Nithya. He's gonna talk about the a general theory of closure invariants in copolar and full stocks radio interferometry. Nithya, you ready?
Can you hear me?
Okay, yeah, we can hear you.
Yes. And my slides, are they in the presenter mode or?
No. Oh, okay, yeah, now it is.
Yes. Okay, great. Thank you. Hello, everyone. My name is Nithya. I'm affiliated with CSIRO now and formerly with the NRAO. And I would like to thank a lot the organizers of this meeting for giving me an opportunity to present our research, which I think could be quite relevant for the ngEHT. The talk will be on working towards a general theory of closure invariants in radio interferometry. And this work wouldn't have been possible without my collaborators, Joseph Samuel, or Sam, who's a well-known physics theorist, and also Raja Ram, who some of you may know already, and he is well known in physics and astronomy circles. I also want to mention that the graphic here was created by Sam's daughter Roshni, and it's meant to encapsulate that we could borrow some ideas from lattice gauge theories and apply it to quantities that we define on triangular loops in radio interferometer arrays. I don't have to go into the detail of the scientific motivation in this particular audience. Closure invariants have been very important in making some significant breakthroughs with VLBI. It was relevant decades ago, and it's relevant today more than ever. And because this talk is going to be a bit on the side of theory, I want to give a high-level summary of what are the questions that we are trying to pose and the solutions that we have got so far. So even though closure quantities have been in use for decades, they have required quite fundamentally different treatments when you deal with triangles as opposed to quadrilaterals, for instance. The way they are constructed is different. And only recently, a polarimetric closure invariants have been worked on using the idea of closure traces on quadrilaterals in a fascinating paper by Avery and Tom, who I hope are in the audience here today. However, it's still unclear when you're using quadrilaterals how you would go about finding a complete and independent set of invariants, especially for an array of arbitrarily large size in the polarimetric case. So what we have tried to do is present a unified treatment for all closure quantities using only triangle loops as elementary units, and we believe we can understand and treat them quite easily. And we have used some ideas from lattice gauge theories and Lorentz invariance properties to understand these closure invariants. And we've provided what we believe is a simple prescription for a complete and independent set of closure quantities for an array of arbitrarily large size. And we've done some numerical checks as well. Now, before I get into the theory aspect, we also want to know what we expect from the theory. What are some of the things that the theory cannot violate? And we go about this by using dimension counting arguments. So imagine you've got so many correlations, and these are in general 2 by 2 complex matrices. And so these numbers are living in some high dimension space. And then you've got some gains that corrupt these visibilities, and they have n matrices, each of them being 2 by 2, and they live in a slightly lower dimension space. Now, if we allow the gains to vary as much as possible and see how they affect the visibilities, we'll find that the changes in the visibilities, the dimensionality of those changes would be slightly lower than the total number of dimensions possible. In other words, the dimensions over which the portion of visibilities don't change would actually give us how many independent closure invariants there could be. Of course, we have to pay special attention to special cases such as, for instance, if you have a constant phase applied across all the antennas, those phases would get canceled out and wouldn't affect the visibilities one bit and so on. So this is sort of what forms our basic idea. Now, let's get into the theory itself. So traditionally, closure quantities have been constructed using either bispectra, which is triple products of correlations. And because that involves a gain and a complex conjugate of the gain, usually the phases cancel out, but not the amplitudes. On the other hand, if you work with quadrilaterals and inverses and ratios and such, then those inverses help cancel out the amplitudes, but not the phases. So we want the best of both worlds, and that's why we've tried to do a quantity that has both the Hermitian conjugate and the inverse in it, and which is also the quantity that Avery and Dom used in the paper. We just designate that using a hat operation for convenience. Now, using this hat operation, if you construct a loop, a closed loop, and the even numbered loop, as shown here, then also making sure that every alternate term is hatted with this Hermitian inverse, then you will end up with a quantity that cancels all the gains in between the terms and is left with only a gain in the front, which is G0, and a gain at the end, which is the G0 inverse. So in lattice gauge theories and such quantities that undergo such a transformation are called covariants. And we know how to extract the invariant information from these so-called covariants by just taking the traces of these matrices. Because traces are preserved under a cyclic permutation, you will end up having invariance by just taking the traces. However, we require an even numbered loop, and the smallest unit there would be a 4-element loop. And there are totally n to the power of 4 combinations possible in general, out of which we know that the independent set is only of order n squared. So how do we extract that exact set is what we'll try to address. So I would describe 4 effective steps to go about doing figuring out our complete and independent set. The first step is to decide on our most preferred antenna, call it, say, ALMA or something like that with the most preferred properties, and call it as our base vertex, 0. And then we find all the independent triangles that contain this base vertex. They're all pinned at this. This is standard process that we do for figuring out our closure phases, for example. And on each of these triangles, we are going to define a term that we call as advariant. This is just our coinage. And an advariant is like a bispectrum, which is a triple product, except that the middle term is hatted. And then we'll find out that such advariants, when they are undergoing transformations because of antenna gains, they transform with a prefactor of G0 and a postfactor of G0 dagger at the end. Everything else in between cancels. And all the advariants only depend on this G0 and G0 dagger. So you've already reduced the problem of dealing with n element antenna gains to just dealing with 1 antenna gain. And for a trivia, autocorrelation happens to also be an advariant. The second step is a crucial step. It is about recognizing that these advariants behave or transform as Lorentz transformations when these antenna gains are applied on them, or they behave as properties that we associate with the Lorentz 4 vectors that we know from relativity. And this happens the following way. You could imagine that an advariant is a general 2x2 complex matrix, and you can break it down into sum of polymatrices. So the coefficients of in front of these polymatrices, if you put them together, it forms a 4-element vector that as shown here. And can be shown that any transformation that has a G0 in the front and G0 dagger at the end undergoes something very similar to a Lorentz transformation, except that there is also one overall scaling factor that we have to account for. A familiar example of such advariant that undergoes these Lorentz transformation in radio astronomy is a coherence matrix, which actually we can break it down as the I, Q, U, and V Stokes parameters. And these Stokes parameters actually happen to be such Lorentz 4 vectors. Why are we so interested in identifying Lorentz 4 vectors? That's because we know that under Lorentz transformation, certain properties are invariant, such as the lengths, and also any inner products between any 4 vectors are also invariant. And this is the property that we'll be using to figure out our invariance. Now, of course, 4 vectors have spanned in 4 dimensions. And so we want to create a basis set for this 4-dimensional space. And the way we do it is we take any 2 triangles and add variance on these triangles. Each of them corresponds to 1 complex 4 vector or 2 real 4 vectors. So by taking 2 triangles, we've effectively constructed 4 real 4 vectors, and this forms our basis set. Among these 4 vectors, you can imagine there are 4 lengths and 6 cross products. So that gives us 10 inner products, which are invariant under Lorentz transformation. And finally, we also consider the rest of the triangles that are in the problem, and each of them again corresponds to 2 real 4 vectors. And we project each of these 2 real 4 vectors onto the existing basis set, and each of those inner products are also invariants under Lorentz transformation. Of course, then there is that one remaining overall scale factor in all of these inner products, which we eliminate by taking of a ratio of all these with respect to any one of them, for instance. So that eliminates that final scale factor. And we end up finding that the number of real invariants in this problem is the same as our dimension counting principle that we started with. We've also done some numerical checks to make sure that our theory is sound. For instance, we've taken input gains and perturbed them and see how the visibilities are perturbed. So we construct a Jacobian matrix that relates the input to the output, and we've constructed the rank of this Jacobian matrix using a singular value decomposition. And we found that the number of ways in which it doesn't vary is agrees with our theory. And similarly, you could also make the inputs as the visibilities and the outputs as the invariants themselves and consider the rank of this Jacobian matrix. And we found that, again, the dimension of the Jacobian matrix agrees with what we expect the number of invariants to be. I've put a star because there are certain special cases. For example, n equals 3 is special, and if you include autocorrelations, that also changes the number of invariants. But I won't go into those details unless someone is interested. So in summary, we've basically at the moment tried to unify the treatment of closure invariance for both copolar and polarimetric interferometry using only elementary triangular loops. We don't need quadrilateral or higher order loops. Everything else can be handled by just using triangular loops. And we've tried to provide a consistent prescription and for determining a complete and independent set of closure invariants for arrays of arbitrary sizes and for polarimetric measurements as well, and has been verified numerically. In terms of ongoing work, we are at the moment exploring how the noise propagates from the visibilities to invariance in these kind of nonlinear quantities. And we're trying to generalize the methodology that was prescribed in Blackburn et al. 2020 to also work with the polarimetric case. And of course, we are also interested in identifying some kind of direct correspondence between some of these closure quantities and the black hole parameters. I think with that, I will stop and take any questions.
Thanks, Nithya. I think we have time for one or two quick questions. I see 3 raised hands, and I believe Aditya is the first one. So please.
Yeah, it was actually a remarkable talk. So I'll ask the quick question here and the longer question in chat. So the quick question is, you decompose into Pauli matrices, right? So these are 2x2 complex matrices. So you have a group structure of SL2C attached to them, right?
Yes.
Cool. Thank you. I'll ask a longer question in chat. Thank you.
Yeah. Okay. Yeah. There is the SL2C part, which is the Lorentz transformation part,
Yeah.
and then there is also the projection part, which is a constant scale factor.
Right. I see.
Yeah.
Thank you.
Okay, Ramesh, please.
Yeah, so Nithya, I
Yes,
heard
hi,
about
Ramesh.
these 2 papers from Rajaram. He sent an email to me, and I
Okay.
read the papers immediately. It's fantastic work. It's beautiful. Okay, really lovely stuff. I had only one place where I got stuck. This is paper 2. I think Sam is also on the Zoom call.
Yes.
Sam's paper, you know, this business about n equal to 3 being special, and it's just that you don't have enough vectors to span the 4-dimensional space. You know, all that stuff I understand mathematically. I couldn't understand where that extra degree of freedom comes from in Stokes parameter language. I mean, as a more practical person, I didn't know how to interpret that result. If you have any insights, I would love to hear it, but maybe it will take too long. We can do it offline.
Okay. I think Sam, since he's here, he might be the most expert to answer this question. Otherwise, yeah, we can take it offline. Sam, do you have any comments?
Yeah, well, you find that there are transformations that don't change the visibilities at all. I mean, you find that there are extra transformations, just like the phase that we talked about. Adding a phase to every gain does nothing at all to the things that you measure. That group starts expanding a little bit. It gains 1 in dimension. So that I can tell you in detail on, well, in some other forum. It'll take too long. I don't want to use up too much time here.
Great, thank you.
Yeah, sorry for interruption. Yes, please, could you move the discussion to Slack, please? And sorry, Dom, and who else raised hand? I don't think we have time for now. Please use Slack. Okay, so now let's move on.
Thanks, everyone.
Let's move on to the next talk. Our next speaker is Mislav. He will talk about probing the origin of AGN obscursion with multiwavelength interferometry from the radio to X-ray bands. Mislav, yes, please. Mislav, are you talking? We can't hear you.
Okay, I lost my unmute button. Sorry about that. Thank you for the introduction. My name is Mislav Balokovic, postdoc at Yale University at the moment, and I'll tell you a little bit about some of my interests, which are more in the multi-wavelength science, but may connect to the radio at high resolution. So in principle, with AGN, we do know it matters a lot what happens at the black hole event horizon, but also we know that structures that belong to the AGN and interact with the black hole ultimately stretch all the way to megaparsec scales through the jets, but not only the jets, but all the other structures, such as the outer accretion disk, the broadline region, narrowline region, and the torus, which is shown here in very simple form in red. But even that part is not as simple as that sketch that we like to have in mind when we think about AGN, where we can't resolve their actual structure with instruments. So the torus itself can be any number of things. I've listed them here on the right, and there's also a number of different geometrical features in this sketch on the left. And of course, it does matter what is going on there. Maybe all of this exists in every AGN, or maybe some things are typical for some AGN and not for others. That's what I'm trying to find out here. What we do know is that 50% or more of AGN we do see through such structures, and they cause obscuration in the X-rays and the optical. We can tackle some of these interests in the X-ray band. X-ray telescopes cannot observe through the atmosphere. They have to be on satellites, and we have a slew of satellites currently in orbit that allow us to cover essentially the whole energy range between 0.1 keV and about 100 keV, and model those spectra and extract information about the geometry. The basic principle of how that works is that the X-rays that come from somewhere very close to the black hole, on event horizon scale, they go into all the other structures surrounding the black hole and get scattered, and fluorescence emits features that you see over here as iron line and Compton hum. Those are the two dominant features. There are some others. And if you can track those features, then you get a handle on the geometry. You see one real example on the right side here, where you see some of the lines and the Compton hump at higher energies. There are theoretical models that allow us to do so. I've built some of those models myself. I'm happy to tell you about it later if you're interested in X-ray spectroscopy. Just the basic principle here. If you have a 90% covering factor of material surrounding the black hole, as is shown over here on top, you might see a spectrum like the red line over here. Whereas if you have a very small covering factor, as seen from the black hole, something like a disk, you would get something like the blue spectrum on the right here. And if in your data you can distinguish the red line from the blue line, all other things being the same, you have a handle on this parameter. However, it's important to note that there's no physical scale to these models. All these is an effect of optical depth. And so the question of scale and what this corresponds to is what motivated this talk. Just a brief example of how this looks when applied to data. In all of these panels, you're looking at a torus covering factor parameter on the y-axis versus the torus average column density on the x-axis. And you see that we can actually place AGN in different parts of that parameter space. In particular, on the right side, you see on the top row some good constraints compared to some relatively poor constraints in the bottom row. But when we put together all these constraints from previous work, you can look at dependence on luminosity and/or Eddington ratio. People have found, including myself in my thesis, that the covering factor, the median covering factor, goes up with luminosity, peaks at about typical Seyfert luminosities, and then drops off towards quasar luminosities. People have theorized about why that could be. There are some ideas up here on the slide, but I'm not going to go into much detail on that. I just wanted to add here that since then, other people have confirmed this is one example where, again, you see the covering factor on y-axis going up, peaking, and then dropping towards higher luminosities. One thing you'll notice is that at low luminosities here, we have relatively poor constraints, which we can improve. These have been snapshot observations that are very, very short, but we have multi-epoch data now that will enable us to constrain this parameter better. Also, by definition, these low luminosity AGN have to be nearby, otherwise we wouldn't have the X-ray data to look at. So there's also a question whether we can perhaps resolve them spatially and constrain this physical scale. Here's one example. In a paper published earlier this year, we looked at local low luminosity AGN, NGC 1052. Without going too much into detail on the X-ray analysis, I'll just say, show this data. We have 4 different epochs of good coverage up to very high energies, and that's what enables us to get very good constraints on the covering factor and the average column density of the torus in this AGN. To look at the physical scale, we turn to VLBI data. Here is an example of that particular jet, NGC 1052, on a sub-milliarc second scale. This is the jet. Transverse to the jet is a band that is highly absorbed. There is some free absorption in the way, and we can associate that perhaps with the torus. So if we take a cross-section along the jet, this is what the x-axis of this figure, and convert this to opacity, then these gray points are the measurements of opacity along the jet. And the colored lines are what if we scale that to a particular scale here, is what our X-ray model would correspond to. I think it's pretty obvious that they don't match. And an obvious question arises whether we can derive a better model that would fit both X-ray data and VLBI data. So we tried a few different options for gradients, for example, and found that a very strong vertical gradient in the direction of the jet, which is shown here in the rightmost panel, would start to match the data both in X-rays, no worse than the original model, and also the radio data. But is there any hope that we can do all of this in X-rays and perhaps have multi-wavelength constraints, more direct constraints that don't depend on somewhat uncertain conversion between X-ray and radio absorption? Yes, in principle, mid-infrared interferometers have been able to constrain sizes of the dust emission to 1 to 10 milliarc seconds. They've been around for a while. The new kid on the block is near-infrared interferometry, enabled most recently by the gravity instrument, VLTI, that has been able to resolve the emission from the torus on milliarc second scale in NGC 1068, which you see their image over here and the best shot at interpretation for what they're seeing. On the left here, I'm showing these torus angular sizes as function of flux in the X-rays for a 25 brightest X-ray AGN. And you can see that it roughly scales locally with square root of the flux, but all of them end up being sort of sub-milliarc second scale out to about 100 megaparsecs. So there is hope that we can perhaps do this in X-rays. In infrared is getting difficult because you need multiple hundreds of meters baseline and large telescopes. It's difficult to build. Whereas in X-rays, you can have an interferometer of a size with a baseline of a meter and achieve the angular resolution of 0.1 milliarc second, even as early as the 2030s. This is something that's been pitched to European Space Agency in the Voyage 2050 roadmap, and may well be possible to do. It's being considered in Europe. And this scale would match very well the continental and global VLBI arrays and observe perhaps jet dynamics and look more directly at this absorption against the jet in the structures that are intervening. Looking a bit further in the future, the same type of X-ray interferometer, if put on multiple spacecraft, could resolve structures as small as 0.1 microarc seconds. That would allow, first of all, any sort of torus in the observable universe to be observed. All of them should be bigger than 10 microarc seconds. But it also allow looking at accretion disks of quasars, for example. And it's not an entirely crazy idea. By 2050s, we might have electronics and stability of spacecraft good enough in the era when LISA will be flying, tolerances are roughly the same. to have an X-ray instrument of this sort in space. So in summary, I mentioned that most structures surrounding supermassive black holes further away are not spatially resolved yet, and that some of that structure can be extracted from data such as X-ray spectra. The X-ray torus, although I've called it the torus as is traditional, it can be many things, but some of the first order geometry descriptors, like the covering factor, we can constrain and see that there's a luminosity dependence to both, to that, and although it's currently loose at both low luminosity and high luminosity ends. I've shown one example how VLBI can help us set a physical scale for the models that we're fitting to X-ray data, and hope that this can be expanded to at least a sample of low luminosity AGN, even with current instruments. But ultimately, I hope that interferometry at other wavelengths will help to directly resolve some of the structures in the future, not only on the scale of the torus, which is relatively huge compared to what we've been discussing here this week, but also on scales of accretion disks, not necessarily only in low luminosity AGN, but also in quasar-like Seyfert type AGN that do not have strong radio emission. And with that, I'll end and take any questions. Thank you.
Yeah, thank you, Mislav. Do you have questions or comments? Mislav, please raise your hand. I don't see any hands raised. Mislav, for the absorption observed with VLBI, are those in which frequency? I didn't clearly.
So this is typically derived from multi-frequency observations. As you go to higher frequencies, there's less absorption. Yeah. So multi-frequency observations are key for this. In considerations of ngEHT, it would be better to have more than a few frequencies, but also the resolution is such that a lot of this work is actually very well suited for something like ngVLA, which has more collecting area and perhaps lower frequencies.
Yes. Thanks. Okay. If we don't have more questions, let's move on. Thank you, Mislav. Our next speaker is Pratik Dabhade.
Yes.
He will talk about giant radio galaxies and their jets. So Pratik, please.
Is my screen visible?
Yes.
Okay, thank you. Okay, so hello everyone. Thank you to the organizers for giving me a chance to speak on giant radio galaxies. I'll be talking about these objects and trying to motivate towards how future studies with ngEHT can be targeted to such objects, as they are the biggest radio galaxies as well as one of the most powerful ones. So this audience is quite knowledgeable, so I don't need to tell you how a radio galaxy looks. Their sizes are much larger compared to the galaxies we see in optical. So often we have this classical picture of jets and lobes. So this is how a comparison chart looks when you compare a radio galaxy with respect to other galaxies of spiral and elliptical type. And if I were to give you a scale of just for you to picture or imagine, a megaparsec is something which can pack nearly 33 of our Milky Way galaxy. And the different scales of radio galaxy has been explored with this particular famous object, which we all are familiar with, MIT7. And this is the general AGN unification paradigm, where we have classified objects as per the viewing angle. So we have blazars which are really viewed at a very smaller angle than quasars and then radio galaxy. We just heard about the torus in the previous talk. So radio galaxies come in all shapes and sizes. Just a minute, I'll just try to move this here. Sorry about this. Yeah. And radio astronomers have classified them as per their features. So we have wide angle tail, narrow angle tail. So, but the one we are interested is the giant radio galaxies. So these were found originally in the early 1970s with the new telescopes then. And since then we have been trying to understand their nature. So this is how a comparison looks when you compare the famous Cygnus A Hercules with the giant radio galaxy. So these are defined as radio galaxies which expand more than 700 kiloparsec in size. The highest we know, it has gone to size of 5 megaparsec, where comparable to the size of a galaxy cluster. They mostly have this FR2 morphology, and they have naturally the most biggest, the largest astrophysical jets for us to study. These also are likely to be the progenitors for this galaxy cluster relics, which we see, providing them the seed electrons. So galaxy cluster relics are the relics which emerge out of when two galaxy clusters merge. So what are the open problems for giant radio galaxies? So we are trying to understand why they are so big, how they are formed, how they are rare, how do they contribute to other surrounding processes. Are they just older counterpart of radio galaxies? Is recurrent AGN activity responsible for their sizes? Do they how their jets are magnetized and stable for such a long range? So do they host more very powerful AGN which is responsible for this, or is it just that they grow in sparser environment, or is it a combination of both? So we need to perform multi-wavelength, multi-frequency study of a much larger sample to answer these questions. So to achieve that, we need to carry out searches from new and old surveys using optical data and sensitive telescope for follow-up. So therefore, we came up with this project called Sagan. Nothing to do with this great man called Sagan, but it's an acronym for search and analysis of giant radio galaxies with associated nuclei. So these are the goals we set out. So we started this in 2016, and these are the goals we set out to address the problems I listed before. So first we had to compile a database of giant radio galaxies known in literature. Second was to find new, because we know they are rare. So from the new surveys, what we can do. Then to study their AGN as well as large scale radio properties and the environment properties, so that we have a clear picture. So these are some of the telescopes which we have used to carry out this work. So this, like I said, back in 2016, this is where we stood. We only knew only 300 or so giant radio galaxies. This is very small number compared to the thousands of radio galaxies which we have known since the 1950s. So first was to compile the data, and that was not easy. So we had to carry out extensive search from the literature, because they were not having same nomenclature. So we identified those candidates, verified their structure, because the older data had poor resolution and confusing sources. We updated the redshift, measured their sizes uniformly, and used the latest cosmological constant to get their sizes above 700 kiloparsec. So we carried on this task until March 2020, and then we were able to carry on with making our catalog for giant radio galaxies to carry out the other goals. So that was searching. So we did this using the new optical data and the new radio survey, like the LOTS, which is from LOFAR. And so all of you probably know what we can do with radio surveys and the new optical data. So this is the LOFAR 2-meter sky survey, which was used at 150 megahertz. And owing to its sensitivity, we were able to unearth a big population of giant radio galaxies just from a 424 square degree area. So these are some snapshots of the giant radio galaxies which we have found. We also found the double-double, which are the restarted ones, and hybrid morphology. We also carried out a search through the older surveys in combination with the new optical data and other complementary surveys for getting the resolution, and found another large sample of 162 giant radio galaxies. So in all, we were able to finally make a complete catalog of 820 giant radio galaxies. That's the largest catalog till date, and using which we carried out the further study to answer these questions about their space density, AGN type, and their similarities or dissimilarities with the normal sized radio galaxies. So that formed the content for this paper. So here we have studied their radio as well as AGN properties like the black hole mass, Eddington ratio, and their accretion mode using a wide range of SDSS and WISE mid-infrared data. So this is the WISE diagnostic, which helped us classify the accretion mode of low excitation or high excitation. And you can see the black hole mass distribution of the giant radio galaxies and the normal sized radio galaxies and their Eddington ratio, which is more or less the same. We also tried to show the disk-jet coupling using Eddington ratio and the jet power scaled by Eddington luminosity. And we can see a nearly tight good correlation showing the possibility of a disk-jet connection. So I'll quickly move. So spectral aging, so we also carried out multi-frequency study with the GMRT to study their ages. So I'll quickly, so this is the highlight which I want to talk about. So from this project, we could conclude that GRGs are not as rare as previously thought of, but they are still rarer in compared to the larger radio galaxy population. They do grow in denser environment, so they just don't grow in sparser environment. They have both high and low accretion mode. Their black hole masses are very similar to that of RGs or quasars. They mostly have very low star formation rate, so probably hinting towards quenching by jets. And their spectral ages, they are really not that old compared to radio galaxy. This is the, so we tried to follow up certain, yep, thank you, giant radio galaxies with GMRT and other telescopes to find, so this, what I show is a giant radio galaxy in a cluster having 440 kiloparsec jet. We have resolved the core at 1.4. And we can see this kind of plasma instability, which could be originating along the jet and finally manifesting into such a large instability. So this is a spectral index. So the future looks promising with all these telescopes coming up. Now the VLBI part of this giant radio galaxy has not been probed in detail. There are only handful of papers which have targeted giant radio galaxies for their study. So here is one example where you can see that if you probe them at VLBI scales, going down to milliarc second, you can see this restarted activity very clearly. We can also nail down the inclination angle and get to know their proper length or very close to a proper length, so their sizes, and so we know how long really these can go. We have no idea currently about their parsec scale, jet and polarization properties. So here is one example where they have tried to do this for NGC 315, and they have not found any high degree of polarization at parsec scale, which is very contrasting to the kiloparsec scale studies. So I'll end with saying that these are one of the most fascinating objects, the biggest and the most powerful, and we could possibly look into them for the future studies with ngEHT. Thank you.
Thank you, Pratik, for keeping it on time. So questions and comments, please. Please raise your hand. Yes.
Yes. So thanks for the nice talk. And I have one question that you said that you have to take the external environment of these galaxies into consideration. And hence my question is, how do you measure the conditions of the external environment along these galaxies, and let's say down to the initial maybe 1 or 10 parsec, something like that? How do you measure it?
Okay, so when I meant when I talked about the environment, I meant because one of the proposed theory for explaining giant radio galaxies, what they grow in a sparser environment. So when I first talked about the environment, I meant the large scale environment, the cluster or the filaments. Where do they grow? If one were to look at the immediate environment on the parsec scale, then we would need multi-frequency studies, especially at the millimeter, to see what kind of gas structure is there using the carbon monoxide and how the jet is interplaying with them. So that's more parsec level physics.
Okay, thank you.
Next question by Ramesh, please.
Yeah, I might have missed this. Do you have estimates of the jet power, mechanical power?
Yes.
These guys much more powerful than normal radio galaxies.
So the way we have computed the jet power is using this 150 megahertz flux correlation Hardcastle's, and not using the usual method of doing it via the X-ray cavities, because the X-ray cavities, they are mostly found in very powerful cluster objects where you see those cavities. We don't have those kind of measurements for all these giant radio galaxies. So hence we use this 150 megahertz flux. And we found that they range from 10⁻42 to 45, 46 arc per second. And they are peaking around 10⁻44 arc per second, the jet powers. And quasars, the ones hosted by quasars, they of course have the higher jet power. About 30% of the giants are hosted by quasars.
Thank you.
Thanks. And I don't see more raised hands. And okay, I think we are coming to an end of this session. Let's thank all the 4 speakers again, and thank you everyone for participating. Yes. So please, if there are further questions, please use the Slack channel. And yeah, now I think we can return to the main room.